from Harvard. So he's going to talk to us about the SYK model, a window into a non-Fermi liquids and black holes. Okay. So
Okay, thank
yeah,
you very much
thank
for
you.
making me part of this conference. So I hope you can all hear me and also see the pointer on the screen. Okay, so I'm predominantly a condensed matter theorist, and I'm going to give you a gentle introduction to the SYK model and some of its connection to gravity. As you'll see, this is just the very simplest case of a gravity theory, the JT gravity theory that you heard about in much more detail in the previous talk with many additional dilaton potentials. And then I will say something about applications to condensed matter systems, which are ultimately connected to numerous experiments in correct, and you'll find that also of interest. Okay, so here's the outline of my talk. I'm going to begin really with very basic things from a time ago. This is really the background to many of the things you heard about in the previous talk. That's be parts 1, 2, and 3, and then talk about more condensed matter systems. So let me just begin, just explaining, what was interesting about the SYK model, even way back in 92 when I first proposed it. And at that time, there was a lot of interest and a lot of realization that there were many condensed matter systems that did not have quasi-particle excitations. So first, let me review a simple model which does have quasi-particles and talk about its properties, and then discuss how that relates to a system that doesn't have quasi-particles. So this is a random matrix model where you have sometimes called Q equals 2 SYK these days, where you just have a random matrix Tij on which particles are hopping, fermions are hopping around at some chemical potential. So if I just thought of this as a one-body problem, then it's just a question of diagonalizing the random matrix Tij. But I want to think of it as a many-body problem where there's some density of these fermions. The total number of fermions is n times q, and q is of order 1, and n is going to infinity. And I want to know something about this system. Now, so the way you do that is just take the eigenvalues of Tij, and you occupy the lowest NQ eigenvalues, and that will give you, the many-body ground state. So we know that if you just have a random matrix, already from the result of Wigner, that it has a semicircular density of states, and the states are spacing 1 over n, where n is the size of the matrix, and you fill up some set of states here up to the Fermi level. Okay. And then you also learn in basic solid state physics that in the limit n goes to infinity, this forms, it's like an example of a metal. It has an entropy that vanishes as temperature goes to 0, linearly proportional temperature, with a coefficient that's given, the Sommerfeld coefficient that's given by the density of states. Okay, and so this entropy is extensive, and it corresponds to excitations of these particles close to the Fermi surface within an energy window of order temperature. Okay, but to connect with the kind of gravity theories that we've been hearing about, we're not interested in this particular density of states, which we would call the single particle density of states. We're interested in the many-body density of states, D of E. This is what Joaquin was just presenting. So D of E is this density of states of all states. And here, the total number of states is not of order n, but of order 2 to the n. So it's much, much, much larger. And any given energy eigenvalue is just the sum of all possible occupied states. And you can see why this 2 to the n, because this integer n alpha can be either 0 or 1. Single particle state can be either empty or occupied. Okay, so if you just take, in this case, I don't know, about 30 by 30 matrix, and you diagonalize it, you get a bunch of eigenvalues. But the total number of many-body eigenvalues is 2 to the power 30, which is a much bigger number. And this is a plot of the many-body density of states here. It looks very different from a semicircle. Okay, so what are some of the features? This is a resolution near the bottom of the band, and this is even finer resolution near the bottom of the many-body band. One important thing to keep in mind is that what's happening at the bottom of the many-body band has absolutely nothing to do with the bottom of the matrix, because the bottom of the many-body band are excitations near the Fermi level, which is somewhere in the center of the matrix Tij. Okay, so we're interested in the bottom of the many-body band. So what do we know about this particular density of states? Well, one thing I already told you, that the entropy goes linearly with temperature. Then by just using some Laplace transform, you can figure out what's the entropy as a function of energy. That's just simple thermodynamics. And the many-body density of states is the exponential of the entropy. Here is also n. So now you see the many-body density of states is e to the power n. And that's maybe somewhere here at low energies, where the energy is extensive, meaning proportional to n, that you get this behavior, where the density of states is exponentially large. But what happens, as you get really to the bottom of the band? Well, if you look at the very bottom of the band, there's something very different happening. The density of states now is not exponentially large. It's actually only of order n. And that's because the level spacing here is 1 over n, whereas the level spacing over here is e to the minus n. Now, why is the level spacing so much larger here? That's really because of the existence of quasi-particles in this model. So if you look at what's the first excited state? Well, the first excited state is you add a particle at the first unoccupied state, or you remove a particle from the first occupied state. And since these single particle states are spacing 1 over n, at the bottom of the band, the many-body states also will have a spacing 1 over n, meaning the density of states is about n. So that's really one of the striking features of the many-body density of states, that it becomes really thins out and has these long tails where the density is very small. And this is where you excite the individual quasi-particles. So this really tells you that you have essentially well-defined single particle excitations and quasi-particles in this model. Well, this is of course free particles, but if you add a weak interaction, this feature would still be true. Okay, so here's the SYK model, where it's very similar to the random matrix model, except now instead of having a 2-body term, you have a 4-body term, and U alpha beta gamma delta. And this is presumed to be a random number with 0 mean and variance U. Okay, so first let me just, let's just go ahead and compute the density of states of this object. What's shown here is actually a numerical computation for the Majorana model, but that's a small detail that's not important for what I'm discussing. So now you see, if you look at the many-body density of states, it has no long tail. There's nothing, it's really seems to be much sharper towards the edge. And in fact, if you look at the density of states over here at low energies, it has this exactly the same term that we had for free particles, square root of 2n gamma e, but it has another constant, which remains non-zero as the energy goes to 0. So this is really the striking feature. This tells you that the entropy doesn't just go as n gamma t as it did for free particles, it goes as a constant plus gamma t. So this constant will then turn out to be, of course, the black hole entropy. For the SYK model, it's a universal number that we computed a long time ago. All right, so this is, and so one consequence of this constant is that if you now look here at the very bottom of the band, it's not exponential, it's not of order n, it's still of order e to the n, even at the very bottom of the band, down to energies which are exponentially small, in fact. And you can just see that from this here. So this tells you that if you take a small window, even of order 1 over n, at the bottom of the band, the total number of states is exponentially large. There's no degeneracy, but there's a very large number of states. And since the number of quasi-particle states, if there were any quasi-particles, would be of order n, there's no way you can think of these many-body states as the sums of quasi-particles. So that's really, from a condensed matter point of view, a very remarkable situation. You have a situation where you have no quasi-particle description of the low energy spectrum. You really have to think about all these different many-body states as interesting many-body states in their own right, and there's no clear relationship between them. They're all orthogonal to each other and involve, total rearrangement of the entire system in the wave function, not just adding or removing a quasi-particle. Okay. In addition to this factor, there's also a square root factor that appears. And in fact, it's known how to interpolate between these two limits. So about in this talk, goes from essentially the square root of E dependence, which is very universal in any many-body system, to this formula with an exponentially large number of states, even at energies of order 1 over n. Okay, so in the next part of my talk is to just give you a bit more information on where this formula comes from, although some of that may be unnecessary given some of the previous talks, but I'm just going to do it anyway. So just to summarize, in the free particle system, you had then a density of state of order n, and now you have a density of states of order e to the n. And that's really the most fundamental difference between the random matrix model of many fermions and the SYK model. And you notice also here, there's no tail like there is over here. There's no tail, and that's because there's, it's basically of order e to the n almost all the way to the bottom. Okay, and the discreteness of the levels is really, in this case, a very much an SYK feature. JT gravity doesn't know about these very precise discrete levels. It kind of smooths it all out. That's the part that's averaged out in JT gravity. Okay, so yeah, so just a few words about where this comes from. So these are the original, SY equations for a slightly different model written down in 93. If you just take this particular model and you expand order by order nu and take the average, you get the usual Dyson's equation, but this is the very simple exact large N limit. The self-energy is basically the cube of the Green's function. So when I first wrote these down, I thought it'd be just a few days to figure out its properties. But there's a huge amount of structure in these equations, and we're still learning new things about the structure of the solution of these equations. Okay, so oh gosh, okay. So you can solve this equation to leading order. Sorry, I can't see some of my own slides. Yeah, okay. And when you solve it, say at mu equals 0, you get the Green's function indicates as 1 over square root of tau. So now you can ask, well, that's the long time decay. What are some of the corrections to this 1 over square root of tau decay? And one way to do that is to do the analog of conformal perturbation theory. So there's 1 over square root of tau, you imagine it's just given by some conformal field theory. And then you add some scaling operator of dimension h with some coupling g sub h. And so you try to figure out what are the allowed values of h. And it turns out that that's quite easy to determine in this, again, in the SYK model. You simply have to solve this particular equation for the 3-point correlator of OH and 2 fermions. So you can see this is some sort of integral equation that you have to solve when you look for operators where the solution is just a pure power law. So that turns out that happens when the bare term doesn't appear, and then you get an eigenvalue equation. You look operators, and you have to solve as a function of h the eigenvalue E is equal to 1. So this was done, I guess maybe first by Rosenhaus and Polchinski You get a tower of states, but the smallest non-trivial value is h equals 2. And this turns out to be very crucial, as later shown by Kitaev and, well, I don't know, later, Kitaev and Maldacena and Stanford. This h equals 2 in the dual gravity theory is precisely the boundary graviton. But in the context of the SYK model, it means that the first correction to this thing decays as 1 over tau, and the tau here, this power 1 here is h minus 1. That's what is generic. And this is something will be very important for us in the results I'll describe, this particular correction. Okay, so now so that's the solution at n equals infinity. That, in terms of the entropy and the density of states, it just gives you the S naught density of states. But now we want to look at density states. Yes, not. If you look at the entropy here, so far I've just talked about these two terms. Both of these terms can come out of the analysis that I've just given you. So now we're interested in the 1 over n correction, this minus 3/2 log t, which is ultimately, when you do a Laplace transform, responsible for the sinh over here. So just a few, then I'll outline some of the steps for the SYK model, how you get the 3/2. And then discuss also very much in an outline the gravitational derivation of that minus 3/2. Okay. So the key actor in this turns out to be in the context of the SYK model, which something that Kitaev and SYK called a time reparameterization soft mode. All right, so where does that come from? So that comes from a essential symmetry of the path integral of the SYK model. So what you do is you introduce replicas, but then forget about the replica indices. So let's not worry about it. You just average over the u in the path integral. When you average over the u, you get this, things with 8 powers of fermions. But very important thing to remember and keep track of is that the times are distinct. It's not an equal time interaction. It's really an infinite range interaction in time. Now that might seem very unphysical, but in fact, the theory is local in time, and it's the replica limit that makes sure that the whole theory is completely local and doesn't have infinite range corrections. It's kind of remarkable how that all works out. Okay, anyway, so ignoring that subtlety, if you just go ahead and decouple this by a delta function. So the way you do that is you first write unity in this way. If I do the integral over sigma, that tells you that g is equal to this quantity. Then when I do the integral, you get a delta function in g. You do the integral over g, you get 1. So this is just 1, but this tells you that that actually g is equal to this, and every time I see this quantity, as I see it over here, I can just replace it by g. And when you do that, then and then you do the path integral over the fermions. So finally, without any approximation, you get this G sigma theory of just two fields, which are functions of 2 times, tau1 and tau2. And there's some action functional, which is quite a mess because this trace log or this log determinant is not anything simple. You can only evaluate it in expansions and powers of sigma. But it's still useful to keep it in this form. Okay, so far this is completely exact. And this is the G sigma theory of the SYK model. And in fact, Kitaev and Maldacena and Yang and others showed, Stanford, that the low energy limit of this theory is in fact JT gravity. But this is, so far, there's no approximation. This is an exact representation of the average properties of the SYK model for any n. Okay, but you can now make some progress. So now we want to take the low energy limit. It turns out that if you look at the saddle point equations, even in the 92 paper that we solved, this particular term makes no difference to the saddle point solution. So if you throw out this term, the resulting action, complicated as it may seem, has a huge amount of symmetry. It's invariant under both time equidistramization, which is sort of like an emergent gravity, and also gauge transformation, which is a baby version of an emergent gauge field. So it has both emergent gravity and gauge fields. And it's easy to check that under this substitution, that the action as a function of G tilde is the same as the action in terms of G, provided you can neglect this term. Okay, now of course that term is there, so this means this is not an exact symmetry of the action. But once you find the saddle point, you want to now, do a integral of fluctuations about the saddle point only on the flat directions. And the flat directions in space are precisely those that perform this time equidistramization. So if this is your saddle point, GS of tau, function tau, function phi of tau, will respectively perform a time equidistramization and a gauge transformation of the Green's function. So you convert this path integral over two functions of two times to a path integral of two functions of a single time. And this is, of course, a much easier path integral to evaluate. So you have to now take this expression and insert it back into this action and figure out what the structure of the action of the functional is here as a function of the time equidistramization and this phase phi. Okay, so that's can be done only in you have to make additional approximations, like take a large QSYK model or something, but you can deduce the basic structure by symmetry and the transformations of the various terms under the time equidistramization and gauge invariance. So if you use those type of arguments, this is the action that you get. This is the famous Schwartzian term for the time equidistramization. And if you're interested in the charge fluctuations and various thermoelectric effects, there's also a term that couples together in an interesting way, the phase field and the time equidistramization. So for a charged black hole, actually, both terms are present. At least, yeah. But it won't be very important for anything I have to say, so just don't worry about it. Okay, so this is then a derivation of the low energy theory, the SYK model. It's the Schwartzian path integral, and as has already been stated by Joaquin, you get the same low energy theory starting from JT gravity, which I will, I'll turn to topics related to that in a few minutes. Anyway, now the amazing thing is that this path integral with this action, even though it's highly nonlinear, can be evaluated exactly. So this particular path integral, when I take this action, is exactly solvable. And that was shown by various people. Sorry, I don't have the references. Actually, first done by Artland and Bagretz et al. And then also by Kotler et al. And then Stanford and Witten and so on. So when you do that path integral and then do an inverse Laplace transform, you get exactly this famous sinh square root of energy density of states. That's what the path integral gives you. This S naught was already computed by us a long time ago. It's just comes from the saddle point. Okay. And you can also see from this analysis that there's this correction here in the Green's function, which I told you about earlier, but that this coefficient here, alpha G, is intimately connected to gamma. These are not independent coefficients. And that's what establishes that this is in fact the Schwartzian mode that gives you this correction that we established using other methods a few minutes ago. Okay, so that's my summary of the SYK model from a condensed matter perspective and what we know about its many body density of states. We know many other things, which I'm not going to cover. and many of these things are connected to this short chain pattern as well. Any questions at this point? Okay, well then I'll go on to the application of this to charged black holes. And here I want to emphasize something that also Joaquin mentioned at the beginning of the talk, his talk, but didn't go into. In fact, this particular low energy action shows up not just in something, seemingly artificial like the JT gravity. It shows up really for a generic charged black holes in 3+1 dimensions. So for here, let me just recall some basic facts about Einstein gravity and black holes in Einstein gravity, going back to the work of Gibbons and Hawking. So formally, suppose you had a theory of gravity and maybe you had a black hole solution and you that's obviously an impossible task because the theory is not well defined. But that didn't stop Gibbons and Hawking. They said, well, let's just look at the saddle point in a black hole background and let's do it in Euclidean time. And when you're doing it in Euclidean time, the solution is all very well behaved, and you simply have to evaluate this action in a geometry where the time circle has length beta 1 over temperature. And so that gives you the free energy of the black hole and hence the entropy. And using this type of calculation, which ultimately is not that complicated once you can decipher it, at least for an outsider like me, you get the famous answer obtained earlier by Hawking by other methods, that the black hole entropy is the area divided by 4G. And so this is the famous Bekenstein-Hawking entropy of a black hole. Today, for this, so the, one surprising thing about this, many surprising things, it's proportional to the area, not the volume, but also that it's finite. There is no cutoff or anything. The total number of degrees of freedom in a black hole, contrary to, if you were just doing quantum field theory, which was, you had cutoff going to infinity, you would have thought that the number of degrees of freedom are infinite. But that's not true. The number of degrees of freedom in a black hole are finite. And the modern interpretation is that the entropy is really the entanglement entropy of these finite number of degrees of freedom across the horizon. And because it's the entanglement entropy, it's proportional to the area, not the volume. Okay. All right. So that's a quick summary of many decades of work in quantum gravity, at least as I understand it. You can also, you can also do this at finite temperature. Oh, no, what about charged black holes? Excuse me. So now you take Einstein gravity, and it'll become clear why I'm taking charged black holes in a minute, and you add a net charge to the black hole. So you have to also include the Maxwell electromagnetism, but you carry out exactly the same calculation, which actually was already in the original Gibbons-Hawking paper. And then you'll find, again, the same formula that the entropy is given by A over 4G. But I'm more interested now in what's called the extremal limit, where you take the temperature going to 0 while keeping the charge of the black hole fixed. And if you do that, then you find that there is, a constant here, and then there's a correction that's linear in temperature. This is still Gibbons-Hawking calculation. So it's constant plus linear in temperature. And I want to make an analogy between that and this result right here. Well, already there, the entropy is a constant. That's the A over 4G term, and a term linear in temperature. So that's exactly this, which comes in the SYK model. So that's, okay, so why is it linear in temperature and why is it constant there? Well, this is ultimately connected to another feature of this charged black hole solution, at least as we understand it today, that it's got a near horizon region, which is ADS2 cross S2. So if you take the solution, there are these so-called Reisner-Nordstrom solution of Einstein-Maxwell theory in this low temperature limit, and so it's a four-dimensional solution. But as you approach the horizon, you find that two of the dimensions factorize. There's an S2, which is just just the surface of the black hole, but at each point on the surface, there's an ADS2. This is the ADS2 metric right here. And there's also an electric field that's making the whole thing work out. And this electric field is, in fact, will be the holographic dual of the phase field that I showed you in the SYK model. All right, so now you can ask, well, at low temperatures, at zero temperature, the entropy is just the area of the horizon. The first correction, is given by what's happening. And I guess this was, I first saw such a statement in the paper by Marlesena and Yang and Stanford, that if you want to now look at corrections to this this charged black hole solution, you can just focus on this near horizon region. So in some sense, this is of course a very old problem. Gibbons and Hawking goes back to 1977. Somebody could have done what I'm going to now describe a long time ago in principle. We just have to find the right degrees of freedom and do the path integral around the saddle point. But I suspect nobody thought that it would be well defined. I don't know. Anyway, so it turns out to be very well defined and gives a perfectly universal answer, in fact. Where am I here? I'm going back and forth, sorry. Yeah, so if you take the low energy limit, as I've just said, you want to take this Einstein-Maxwell action and reduce it to some effective action, which is in 1+1 dimensions. And this turns out to be exactly JT gravity with a few twists that you can read about in one of my papers. And so the gravity itself is, of course, descends from the Einstein gravity. What about the dilaton? What is the dilaton? Well, the dilaton is basically the radius of this S2. So that also has a degree of freedom you have to keep track of. And the fluctuations of that radius, which is pictorially represented here, this is not a very good picture because this direction is not time. But anyway, the fluctuations in R sub h is the dilaton. And in fact, you only need to worry about the value of the dilaton at the boundary, which is the kind of pictures that Joaquin was just showing you. Okay, so you essentially reduce the whole thing to JT gravity, and then you can do the path integral, and JT gravity becomes essentially by fixing gauge boundary graviton theory with exactly the same theory I showed you earlier. Now the coupling constants gamma and K are related to various properties of the black hole solution. There are precise relationship between them and the coupling constants of Einstein-Maxwell theory. And so you can do the path integral, and then you get, as before, the 3/2 log T correction. So therefore, so now we have a correction to the Gibbons-Hawking result, that the black hole entropy is the Gibbons-Hawking result, which is this one right here. And then there's a corrections minus 3/2 log T. And so this thing is about a 1/g, this is about a 1. Okay, and so what we see is that there's really a universal correction, which is independent of what the actual UV theory of quantum gravity is, whether there's strings or not. It doesn't matter. Both the first two terms for a charged black hole in extreme limit are entirely independent of the UV structure and given by precisely these two formula. Okay, there's a constant inside the logarithm that's sensitive to UV, but not the coefficient. Okay. Right. Okay. So this 3/2 log t gives you this density of states. Here's an actual numerical diagonalization which has exactly this density of states of the SYK model. Okay, so one other point I think it's worth making. This is actually also work by Joaquin. I don't have some other references. I guess there were a few references over here. What about supersymmetric black holes? So one thing you can do is solve a supersymmetric SYK model. And for the case of n equals 2 supersymmetry, you find a very, very different result. What you find is that there's a huge delta function at 0 energy at the ground state. And the strength of the delta function, the total number of states in the delta function, is exponentially large. In fact, it's e to the Hawking entropy, A over 4G. Then at finite energy above a small gap, there's a continuum of states, just like in the ordinary SYK model, with some cinch-like function. So there's this. So what you notice really, especially, is that there's this degeneracy of states, which is coming from ultimately from the supersymmetry. And this degeneracy is entirely absent in a more generic black hole. There is no degeneracy at all. It's just a whole continuum, which has a small spacing, exponentially small. Okay. All right. So that's all I have to say about black holes and things I don't know that much about. So now I'll talk about condensed matter. Of models which are cousins of the SYK model. In fact, the original model that we looked at, because it's much closer to issues in condensed matter, which I won't go into. But I hope to just interest you in the original model that I looked at with Jim Rouillet in '93, which is this model here. So this is a quantum generalization of the Sherrington-Kirkpatrick spin glass. So the SK spin glass was for Ising variables, sigma I, sigma j, with some random couplings, Jij, which has 0 mean and mean square variance, j squared. And that's the original SK spin glass, which was eventually solved by Parisi using replica symmetry breaking in a spin glass state. And was a starting point of a lot of work, including neural networks, and in some ways the father of a lot of machine learning work these days. But here we decided to look at the quantum version of it. Just take the SK model, take SU2 spins with SU2 spin symmetry, a so-called Heisenberg exchange, spin a half. But that's it. Okay, this is the problem that we'd like to solve. Okay, this problem is still not solved today. There is no exact solution. It's much more difficult than the SYK model, but it has a lot of limits in which it reduces to physics in the SYK model, which is in fact what we did in our first paper. Okay, so, but before I tell you about its solution or what we know about it today, we can make some guesses. So first guess would be that even if it's quantum, in the end, things look classical. That it's just like the Sherrington-Kirkpatrick spin glass model. So what at 0 temperature, you can define what's called the Edwards-Anderson order parameter, which says, looks at the correlation function of a single spin on the same site. And if there's a spin glass, meaning the spins have some memory of what's going on, all the way up to tau goes to infinity. And so this average value of any given site, even for a single sample, will be non-zero. And that's the Edwards-Anderson spin glass order parameter. So it may well be the quantum problem also has this feature that this thing is non-zero. Okay, so that's one possibility. The other possibility is, no, that's not true, that it's a spin liquid. So what happens in a spin liquid is that the spin correlation function, which I'm now calling chi of tau, decays as 1 over tau. and goes to 0 as tau goes to infinity. And where does 1 over tau come from? Well, this came from a solution where you generalize the SU2 symmetry to SUM and then send M to infinity. The number of spins is N, which has already gone to infinity. But this large M limit you can rewrite, you can obtain by writing the spin in as a bilinear of 2 fermions on the same site with this constraint. And now you see if I write this thing as 2 fermions and put it in here, I have 4 fermion terms with some randomness. It's not exactly the SYK model, but it's at least looking similar. And it turns out that when you take the large M limit and look at the saddle point equations, the saddle point equations are identical to the SYK. Well, really the SY equations, that's why I put K in bracket. You get exactly the same equations between the self-energy and the Green's function. Okay, so at the saddle point level, these models are the same, this large M saddle point. So now we can use model. So I told you before that the G of tau goes as 1 over square root of tau times 1 plus a constant times 1 over tau. And you take a Fourier transform of that, the spin correlation function, which is the product of G, will have a sine omega, that's the Fourier transform of 1 over tau. And this mod omega is the Fourier transform of 1 over mod tau, the correction, and so on. In fact, you can go to quite a high order in this conformal perturbation theory. And so that's the numerical solution of the G sigma equations, and this is the theoretical expansion, and it really works very beautifully. And this linear dependence here, this mod omega term, is precisely the boundary graviton, okay, in this large M theory. All right, so that's for large M. That's not actually the model we were interested in when we started looking at this. It's just the large M limit of it. What about the actual model? Well, so now there's been, in this recent paper, we just did an exact diagnosation of the SU2 model. And what I want you to notice, so this is the same chi double prime of omega, is that there are 2 features here. There is, in fact, a delta function peak developing at small frequency. So that tells you that it's a spin glass. And in fact, this is the Edwards-Anderson order parameter. It's around 0.02, quite small, but it's non-zero. This is from exact diagnosation of, I don't know, 20, 30 spins. Not 30, but smaller than that. Okay, and averaging over many hundreds of samples. But also interesting, if you go to finite frequency, you have this red line. The red line here is, in fact, just that line over there. And that also seems to fit the data very nicely at higher frequencies. So you have a spin glass at very low frequencies, but it's not a classical system. It's only a very small correction, but you have this quantum SYK behavior, this SY spin liquid behavior at higher frequencies. It seems to fit the general behavior. And if you believe this, then this is actually this fact that this is this linear and omega term here is in fact observation of a boundary graviton, okay, in this particular model numerically. All right, so what we seem to have is a coexistence of spin glass order at very low frequencies and SY spin liquid behavior at higher frequencies. So what we need, and this is actually what we're working on now, is a theory that combines both. So we want to take the SY model and put in some spin glass order. That's what the actual model that we're studying behave like. So what you end up having to do is you have to include the spin glass order parameter in your theory. So in a quantum theory, the spin glass order parameter is a function of time. And you have to keep track of these replica indices now. You can't throw them out. And there's 2 ways to define from these from this kind of QAB, which is defined to be, basically the. I guess I realized I didn't define it. It's just related to the spins in 2 replicas. It's SA dot SB. in two replicas. Sorry, I'll make that correction in the slides that I upload. So if you take the off-diagonal elements of this QAB, that gives you the exozyme as an order parameter. This is the quantum thermal average of the spin squared, and then you take the disorder average. And this is the 2-point correlation function, and that's the replica diagonal term. And these are two different ways of defining the order parameter, and they both have to equal to each other in the limit of zero temperature. That's an important consistency check on the theory. So that's the field you need, this QAB spin glass order parameter, to define the spin glass order. And to define the spin liquid theory, I already showed you need the G and the sigma. So you need to extend the G sigma action for SYK to this G sigma Q action. This is what we figured out with Main Christos and Felix Hale. And this is something that we are working on and trying to understand the numerically observed coexistence of spin glass order with spin liquid behavior. Okay, and finally, let me just finish by just showing you some more numerical data, which we also understand at some level, but I don't, that will take you probably too deep into into condensed matter stuff. What our ultimate motivation is really not to understand this model with spins interacting. We want to actually have the electrons move around. So we think of the spins as made up of electrons, and then the electrons can hop. So you've removed some, you have some empty sites, and then the electrons, the empty sites can move around. So the total number of fermions is, or electrons is not 1 per site, it's 1 minus P, and P is what's called the doping level. But you assume that you can never have more than 1 electron on any given site, and this is what makes the problem very complicated, this constraint. Anyway, so I won't go into any of the, we think we understand quite a bit more about this model now. I'll just show you some numerical results by different methods of solving the analog of the G sigma equations for this model. Okay, so I showed you this chi double prime of omega, how there was this delta function peak at low frequencies, and high frequency it seems to have this graviton-like behavior. So now we start removing some particles, doping the system. And this is what happens. You find that this peak disappears and in fact is not present above some critical doping. So that's very exciting. And right near the critical doping, which is perhaps this red line here, it's a pretty good fit to the spin liquid behavior all the way. So the pristine SYK behavior seems to be present only at this critical point between the spin glass state and some other state at larger P, which is in fact just a Fermi liquid. In fact, it's just very similar to the Q equals 2 SYK model that I began my talk with out here. So here there's a spin glass, like in the SK model. Here there's a Fermi liquid, and in between is the SYK critical point. So here's in fact a phase diagram with all of that worked out in a somewhat different analysis of a very closely related model by these people at the Flatiron Institute. There's the spin glass, there's the Fermi liquid, and then at finite temperature, there's this whole regime which is controlled by, it seems from the numerics, by SYK type physics. So in the application of the cuprates, which have a very similar phase diagram, this would be the strange metal or the behavior with linear T resistivity, which in fact this model also exhibits. Okay, so this spectrum that I showed you earlier is this point here at 0 doping. Then this behavior is what happens as you move up here. And then finally, you can look at the temperature dependence of, say, some kind of electron scattering time. And you see this linear, this so-called Planckian behavior with 1 over tau star going as some constant times KT over H bar. And there's an analogy between this time and the lifetime of black hole quasi-normal modes, which also have a similar dependence on the temperature of the black hole. Okay, so to summarize and conclude, so the SYK model is essentially a unique solvable model without quasi-particle excitations, exhibiting thermalization, many-body chaos, in Planckian times, and lots of other interesting properties, many of which are largely independent of microscopic energy scales. The low energy theory is basically the theory of JT gravity of this model, as you know. And the quantum fluctuation of the JT gravity have actually very interesting consequences even for the SYK model or the SY model, spin susceptibility with this behavior that's seen in numerics, and this universal correction to the black hole entropy, even for generic charged black holes in Einstein gravity. Right, so then I told you about the spin glass type model, which actually turned out in the quantum version, show both spin glass order and and once you dope them, then the whole phase diagram starts looking even, almost exactly like observations. But I should, of course, caution to add, this is for the random model. That's not the real world. Has some randomness, but not so much randomness. And understanding why this model does so well is really something that we need to work on it more. So, thank you. Yeah, I'm happy to take any questions.
I have a simple question.
Sure.
So when you add the spin glass order to the large M model, so it's just a basic question. So you're not going beyond the large M limit. You're looking at the different saddle, but still at large M?
No, you do have to go beyond the large M limit. In the large M limit, there is no spin glass order.
Okay.
So if you notice here, the free energy, I've taken the saddle point with respect to M. And so the dependence Q is as a saddle point. But in principle, I still do have to date the path integral over G and sigma, or there should be a capital D there. You have to include some corrections. You cannot, if you just take the saddle point with respect to M, you just get back the SYK equation where Q is just equal to GG and there's nothing else. But you have to go beyond that. And yeah, that's something we've just understood in the past few weeks. And you have to keep some corrections from the 1 over M correction for terms. And that will help you get the spin glass state that you see for smaller M. After all, you only see that M equals 2. I mean, that's the only thing that's been studied.
So if you go to 3, I don't know.
I don't, well, we don't know. Nobody's looked at 3. But no, actually, what we already said this in our, when we said this in the 99 paper. So if you think it as a function of temperature, so for example here, in this numerical study, as you lower the temperature, there's a critical temperature below which there's a spin glass. This is an actual phase transition here that you can see in the numerics. So you can ask what happens to this temperature as a function of M. So this is for M equals 2, that's the temperature, 0.06 times J. But what we can show, we showed already in the 99 paper that the temperature is e to the minus square root of M. That's always non-zero, even as M goes to infinity, but it's exponentially small. Yeah, so in fact, it's only exactly at M equals infinity that you get the SYK behavior, but the moment you make M finite, there's a very, very small temperature at which you do get spin glass order. Yeah, so there's no critical M. I don't think there's a critical M. And so now we are trying to include, this little delta function in the full theory. It's still small, and so one hope is that you can expand in the size of the delta function. That's what we're working on.
I see. Do you have any thoughts about what do you have to add to JT to have some behavior like spin glass?
To get spin glass, I don't know. I mean, I guess Felix has worked on things like that, right? You have these. You have to have many degenerate classical solutions in some limit of your gravity theory, and I think there are certain black hole states which have that, right? Apparently, yeah. But right, you need many classical solutions of gravity, I believe. So Felix has a paper with recently on some of this. I mean, I guess it goes back to some old work of Mardassin and Strominger, where you can get many multiple black hole solutions, and you can move them around without changing the energy. Apparently, that might be connected to some of the spin glass physics. Yeah. Yeah, but that's an interesting question. Yeah, I don't know much about it. I don't know anything about it, but Frederick Denef and others, in fact, have been writing papers on that type of thing.
Yeah, now that you mention, I think I remember seeing Felix paper. Yeah, fragmentation thing. Okay, yeah, thank you.
So, you know, I think there's more work to be done there. Even here, actually, for the SY model, you know, coming back to this 25 years or more after the original paper, we finally, I think, trying to understand how to do this properly. Well, there was another paper on the quantum spin glass with Georges and Parcolet using bosonic spin-ons, and that's in the limit where the spin glass peak is very strong. Then we can also understand everything. But we want to work in the limit where the spin glass piece is weak, and that's what we're doing now. Yeah.
I see.
Okay, well, thank you very much. Yeah, okay, I think I stopped roughly on time. Okay. All right. Thanks a lot.